So this video is going to be a little bit longer if you haven't already noticed. I'm going to slowly work through some of the different things that we can use in proofs to prove things congruent or to prove things parallel. It's going to be slow going, and I'm really sorry for the long notes. Take your time with them. I'll put out a reminder that it's going to be long. Just take it easy, okay? They're going to be long. So, page 59. Ways to, I want to call it ways to use. Topics used in proofs. Okay. So, let's turn in our books, page 59. And I'm going to try to work through this really slow so that it's not confusing, so that you don't need me to re-explain it to you. So our objective is still to create logical proofs. Logical proofs to justify geometric ideas. I can't remember what that middle word was. To justify geometric ideas. So here are some properties that we might end up using in a proof. Property 1. Segment addition. So what segment addition means is if I have some diagram, let me grab another colored marker here. Okay. Let's say I have some segment. And what I can do is I can say that AB plus BC equals AC. So pretty much what segment addition does is it says it takes two parts. When I add these two segments together, I get the whole segment. Okay? We can also talk about segment subtraction. So AC minus AB is BC. So that's something that we can use in proofs to prove two segments congruent that are part of another segment. So let's say I had this proof and this drawing. So let's make this drawing. And this is what is given. Suppose I knew that AC is equal in length to BD. And I want to prove that AB is equal in length to CD. You're saying, Mrs. Northrop, why are you using equal and not congruent? Well, equal talks about values, and I can only add and subtract with values. I can't add and subtract with shapes. So here I am adding and subtracting with values, and notice I'm not putting the little line over the top, because when I don't put the little line over the top, it means that the segment is equal. Or it means that we're talking about the distance, excuse me. Okay, so if I wanted to do this proof, I would start with my givens. All right, so what do I know? I know that this whole length, AC, is congruent to this whole length, BD. So I'll mark those congruent. And I want to get that this length and this length are equal. So the idea here is if these two lengths are equal, if I take this part out, which is part of both of the lengths, if I take out BC, which is part of both of the lengths, I get AB and CD. And if BC is equal to itself, then these two parts should be equal. So I'm going to use the reflexive property and some other things to help me get there. So I'm going to say that BC is equal to itself first, and you'll see why in a minute. Then what I'm going to do is I'm going to say that AB is equal to AC minus BC. And this is true, other than the fact that it's obvious, but we have to have a reason for it being obvious. This is true because of segment subtraction. So now I have this statement. I also want to say that CD is equal to BD minus BC. And what I'm lining up to do here is I eventually want to get that AB and CD are equal. That's what I'm trying to prove. So I'm trying to get them equal to the same thing and use some substitution here, or even use the transitive property here to help me out. So I know that AC and BD are equal because I already said that. I know that BC and BC are equal because I already said that. So since BC is equal to itself and AC is equal to BD, these two expressions on the right are equal to each other. So by substitution, since these two things on the right are equal to each other, this whole side of the equation is equal to each other, these two things on the left are equal to each other. We can say this by substitution. And if you're having a hard time seeing why that's logically true, let's try it arithmetically. Okay? Let's say AC is some length. We'll count it up as 1, 2, 3, 4, 5, 6, 7, 8, 9. And BD is the same length, 1, 2, 3, 4, 5, 6, 7, 8, 9. I know that BC is equal to 4. So how would I prove that AB equals CD? Well, I know that AB, by segment subtraction, is AC minus BC. So all of AC, take out this part, and I have AB. So AB must be 9 minus 4. So AB must be 5. And I know that CD is BD minus BC, which again is 9 minus 4, which is 5. So therefore AB and CD are equal. Now this is just an arithmetic example, kind of a mental check for myself to make sure this is true. This is the proof. And what the proof does is it shows us that this always works, that AB is always equal to CD for any values here. This is just like my little explanation as to why this works in my brain. But this is the explanation for why this always works no matter how long these lengths are. And this is how we would use segment subtraction. In addition to segment subtraction and segment addition, there's also angle addition and angle subtraction. And I misled you guys earlier. So let's draw that picture again. And draw a picture of an angle. And then tack another one onto it. And what I want you guys to notice is that this is not an angle bisector, okay? Not an angle bisector. So when I do angle addition, angle BAC plus angle CAD, so this angle plus this angle is equal to the whole big angle. And these two angles over here are not necessarily equal. This could be like, 40 or 30 degrees, and this could be more like 60 degrees. They're not necessarily equal. The whole angle, well, maybe it's more like 70 degrees because it's more than a 90-degree angle here. The whole angle is 100 degrees, but just because I can add them together doesn't make them equal. Okay, so angle addition says you can add two adjacent angles together and get one larger angle. Okay, and angle subtraction says that angle BAD minus angle CAD is equal to angle back. Okay, so it's the same idea as segment addition and segment subtraction, except for I'm working with angles. Okay, so some other things that we might need to know that are dealing with sides is perpendicular angles. Okay, so this symbol, or perpendicular lines, make, right angles, and all right angles are congruent. So there's not like a name for this property, it just is. So perpendicular lines make right angles. So if I had AT perpendicular to BZ, that might look like this. And they need a J. Okay. And all the angles around here are right angles, and they're all congruent. So the kind of cool thing about this is I can work with supplementary angles as well. So I could talk about supplementary angles and linear pairs as well and get into this. So linear pairs are supplementary. So a linear pair is any angle that makes, when I add them two together, when I add any two angles that when I put them together, I get a straight line. Okay, so angle XQY plus the measure of angle YQC equals 180. And Y, this would be my statement, and my reason would be linear pairs. Okay, so something kind of neat happens here, and this is how we're going to prove that all right angles are congruent. So here's the idea. I'm going to be given that AT is perpendicular to BC at D. So I'm going to draw this picture. Okay, and I want to prove the angle ATB is congruent to angle ATC. Okay? So, first thing I want you to notice that this perpendicular line does not mean bisect. What it means is that these two lines form a right angle. Okay? So, I'm going to prove that this is true. They're perpendicular. All right. So step 2, I'm going to talk about these two angles now. Angle ATC and angle ATB are right angles. And why are they right angles? Well, that's the definition of perpendicular. Okay. So now, I'm going to say that the measure of angle ATC equals 90 degrees, and the measure of angle ATB equals 90 degrees. And why is that true? Definition of right angle. Step 4, the measure of angle I can just say angle ATC is congruent to angle ATB because they have equal degree measure. And transitive property. So what I did is I proved these two congruent. All right, and now that we have this proof, we don't have to write out this proof again. So if I have these two lines are perpendicular, I just need to say that they're right angles, and then I can say that they are congruent. And I can say that they're congruent because all right angles are congruent. Okay, so this is the reason why this works. All right, I'm going to pause here. This is for Monday night. The next video will be for Tuesday night, and all I'm going to do in the next video is just turn the page.